I start back again from at the stretcher point I had stopped last time. Let me start, complete the stretcher part, and here I go. So, I had stopped at the point where I said there is an ellipticity which is brought about because of the stretcher. There is a kind of astigmatism which gives rise to this ellipticity, which is an inherent part of any grating stretcher. Okay. So, now here actually I gave you some of the aberrations that come about, the reasons for those aberrations. Aberration means not getting a completely circular beam and such, basically not getting a completely circular beam. Now, there are some other problems too in it, which are more important than not getting a circular beam, that is spectral clipping. Suppose I have this elliptical beam and all your spectrum is spread across this cross section. So, if I do not have a lens here of the telescope which has a wide, very wide lens, I am going to get some of these spectrums will get lost, basically get lost physically. So, suppose that whole beam fills up this place, it will be physically lost. And then getting such large lenses is not very easy. Okay. So, there has to be some way where I can avoid that. How can I avoid that? I can change the number of rulings on my grating. So, this as an example, say a stretched pulse from, I am trying to get from 200 femtoseconds to 100 nanoseconds. So, I have this concerns the ND glass. I have taken ND glass as the experimental laser. Okay. And some of the typical gratings come with 1800 lines per mm. Okay. So, I use some grating of this kind. So, 1800 lines per mm will give you a very large dispersion, while suppose I change it to 1200 lines per mm. Okay, it does not seem much, as though nothing much has changed, but then it will give you a much less dispersion. If you see here from the equation, incident is this and diffracted is this. Okay. And it depends on the groove spacing. So, if I have a bigger groove spacing, that means number of lines per mm is reduced. So, D becomes larger. Okay. My that wavelength, and I know which particular wavelength. I do not know if I told you before, m is the order of the diffraction, it is an integer, but for the moment we are talking about m equal to 1, first order diffraction. So, if you can see for a particular wavelength, say yellow frequency within that bandwidth, if D is large, okay, then my sin theta D becomes small. So, theta D is also small. That means with a large groove density, you get larger diffraction. Your diffraction angle becomes more and more. Okay. But the downside is what I have given here. If you take 1800 lines per mm, you will get 200 femtoseconds to say 1 nanosecond. And if you take 1200 lines per mm, you will get 200 femtoseconds to 600 picoseconds only. The desired one is 1 nanosecond, but you are getting 600 picosecond. So, if I reduce the number of lines per mm, I will be able to avoid the spectral clippings here, because it is not such a wide cross section beam in the spatial realm. But then I have to compromise on the pulse length. So, it is a kind of trade off between the number of lines and the spectrum that you are losing, and if you lose the spectrum, your final compression is not that good. You want to conserve that spectrum which is there. Okay. So, it is kind of a trade off, and then maybe at some time, and you get some self phase modulation and Kerr effect even within this lens. This also gives some amount of dispersion. You know, the material of this, just like in optical fiber, the material is causing the dispersion. Here also, even in this lens, it will do that. So, it is a balance between all these parameters which you have to adjust in your stretcher. Okay. So, here I put down, generally it is a double pass configuration which you have understood, and here I write achromatic lenses of focal length 60 centimeters. This is for a specific design. What do I mean by achromatic? By achromatic I mean this lens should be coated so that some dielectric coating, so that all the frequencies that are there, all the wavelengths that are there are not getting lost. It is allowed to pass through. Okay. So, I need a coating, all those frequencies should pass through. It should not be that some of them are not allowed to pass through. So, you lose your spectrum, you do not want to lose your spectrum. So, they are achromatic lenses, and the gold coated, these gratings are generally gold coated, where you get the best reflection. Gold coating always gives the best reflection. And holographic gratings, they have ruled lines like that, but some it is created by a different means instead of actually mechanically ruling the lines. Why they are holographic? So that the phase front is good, phase front is not distorted by the grooves themselves. Okay. These are some details, only if you are actually designing this, you have to take these into consideration. So, the achromatic lens part is important. You do need it coated, which allows all that frequency to pass through. Okay. So, this is the stretcher. Okay. So, at the end of the stretcher, assume that I have got a nanosecond pulse. Okay. So, I have got a nanosecond pulse, but my work is not yet over. I have just done this portion, the stretching part is over. I have to still do the amplification. I have a long pulse and it has to be amplified before it is compressed back again. So, I have finished off this stage, I have to come to this stage. Okay. So, as in a long pulse also, you have seen amplifiers, it is amplified in, and now we do have a long pulse, it is amplified in all different kinds of amplifiers, which I have described previously. Now, what I have not described is a regenerative amplifier. Okay. So, a regenerative amplifier is slightly different from the others. So, I have a regenerative amplifier. Why is it used? It is used because the output pulse energy, after it has stretched in time from the oscillator, is very, very low. It is in the nanojoule or the picojoule level. It is very low. So, if I had just one amplifier and let it pass through, it would not have extracted much energy. So, I would need many stages of these amplifiers in order to extract energy even in the millijoule level. But then I can compress all these amplifiers into one, which is called the regenerative. That means from one medium itself, it's a multipass, something like a multipass. You multiply pass that laser beam along this, and in one stage itself you are able to increase from the nanojoule or the picojoule level of the pulse to say around millijoule. Okay. So, maybe nanojoule or picojoule, you can go up to millijoule level. If you have passed this pulse through that, that is the whole idea of having a regenerative. That means single gain medium is able to produce a pulse of a millijoule. So, why not go in for it? Okay. So, how is this different from a multipass amplifier? You have seen the multipass amplifier before, either 3 passes, 4 passes or 10 passes, which I have described before. While this is more like an oscillator. Okay. It is like an oscillator which has 2 mirrors, and you have a gain medium, and you multiply pass this lasing, and then you take out the output. Okay. Something like an oscillator, having 2 mirrors on the 2 ends, and within the same spatial domain of the active medium, you are passing that. It is going through the same spatial domain, okay, the pulse or the beam. It is going through multiply until it reaches the energy that you desire. Okay. Okay. So, that is what. So, here I have 1 mirror here and 1 mirror here, and I have 2 Pockels cells. Okay, you have to remember what those 2 Pockels cells do. If you remember, the Pockels cell acts something like a shutter. It allows one pulse to go in or not, does not allow. But what is the technique it uses? It uses the technique of rotating the polarization of the pulse. Okay. So, try to recollect your Pockels cell description that I gave before in a pulse laser system. In fact, out of the train of pulses, we have to select one pulse before we go into this amplifier. So, even that uses a Pockels cell. So, I have a train of pulses here, which I showed before. At the end of it, I place a Pockels cell. And the moment this first pulse comes in here, I open the Pockels cell. Okay. And the moment the second one is trying to come in, I block off the Pockels cell. How do I open and close it? By just applying a voltage. When I apply the voltage, the polarization of this pulse rotates. Okay. And I have a polarizer analyzer on either side, if you remember, and the analyzer does not allow the pulse to go through. So, Pockels cell is like a shutter, okay, which uses the fact that the light that is coming in is polarized light. So, here I will just show you what exactly it does. So, this is my input beam, okay, and it falls on a thin film polarizer. TFP is a thin film polarizer, basically just a polarizer. Okay. So, my input beam may be a polarized light. This acts, if this is a polarized light, then this acts just like a mirror. And if it isn't, if this is not a polarized light, then the thin film polarizes that light. So, only one polarization is allowed to pass through, is getting reflected here. Remember the 2 polarization, they are perpendicular to each other. Sometimes they are called P and S polarization, or it is like the E wave and the O wave. Okay. So, P and S is quite often used, they are perpendicular to each other. So, say the P polarization has come here and it gets reflected. and it goes here and it comes to the Pockels cell. It rotates that p polarization partially. It goes to this mirror and then it comes back. Okay. Then it rotates it once again. So, it has changed its polarization from p to say s. They are perpendicularly polarized. Since it is perpendicularly polarized, it just goes through this thin film polarizer. If it wasn't, if there was no rotation, it would have just reflected off. So, this is called seeding of the amplifier. That means, this is the seed pulse which has been able to enter this amplifier. How? Through manipulating the polarization. So, then it goes through here, then it goes through this Pockels cell. Again, this rotates it in some way if it is on. If it is off, it just lets it go through, and then it keeps on traveling here and here and here. And each time it travels through the gain medium, it collects up a little more energy, until you know where to stop, and that time you put on this polarizer. Till that time, this is not on. The moment you put on this polarizer, it shuts off, it rotates that, and then the pulse just comes out here, okay, on this. PD is the photodiode which detects that pulse. Okay. So, here is the input and here is the output at the end of say 100 passes or 50, 60, 100 passes it goes until it reaches, it has extracted all the energy it can from the from this medium. Okay. So, I have a photodetector here and I have a photodetector even here. This mirror allows some leak pulse to go through. Okay. We do not want it to come out, but then you never have a 100% mirror. So, some part of that pulse is going out and we are able to detect that pulse or the growth of that pulse in this. So, in short the regenerative cavity is, that is why it is called regeneration. It regenerates the energy of the seed pulse. It increases its energy and it works somewhat like an oscillator, okay. And then you have the amplification. Now, the problem with this regenerative amplifier is, so I only want the seed pulse to amplify, but if you see the configuration, it is like an oscillator. So, you cannot prevent some of that spontaneous emission which is there in this glass rod, Indi glass as I have taken here, Indi glass silicate rod, this is the active medium. I have done that and you can't prevent that spontaneous emission from growing inside this cavity. It keeps growing inside that cavity and it is adding on to this seed pulse. So, here I show it in a, this is the picture that you get on an oscilloscope which is attached to this photodiode. So, this greenish kind of thing gives you an idea of how this seed pulse is growing inside the cavity. There are a number of lines here, okay, how it is growing. But at the same time, this detector is also detecting another pulse that is growing here, which is shown here, you know. You have another pulse that is growing here, which is different from the growth of the seed pulse. And this pulse is in the nanosecond scale. Now, your seed pulse is also in the nanosecond scale, but I really do not want this pulse to be here, because it is adding a kind of a distortion to, it does not have the same spectral composition as the seed pulse, and I do not want that. So, it is my ideal seed pulse that I took out from the oscillator is getting disturbed here. So, this is at this is a recording on a oscilloscope at this point. This is a photodiode which is recording. So you have these number of round trips in this cavity, and each one is shown by this line. And if you can see at the bottom, there's a slight thing which has happened, which is actually this. It's reduced a lot. So most of it is the seed pulse. So what it is called is, in this you have the Q switching plus the seed pulse amplification. So this part corresponds to the Q switching. If you remember, when I described the Q switching of any lasing medium, you have a shutter which opens and closes at a particular time, and your the Q switches from high to low. Okay. And your Pockels cell here is acting like that shutter. This PC1 and PC2, though this is a kind of thing which injects the seed pulse, but it is also acting like a Q switch shutter. That is why you get a Q switched plus the seed pulse, but what I desire is only the seed pulse. And when you get a picture like this, when this Q switched pulse is almost negligible, it is called complete seeding. So only my seed pulse has got amplified. So this is a kind of a disadvantage in a regenerative amplifier, where you get this additional spontaneous emission which is amplified. Okay. So you want to eliminate that, but then okay, it is there. So the advantage is, in one stage of an amplifier you can get a large extraction of energy and increase the energy, but at the same time you are adding some distortions in your seed pulse temporal profile because of that Q switched pulse or the amplified spontaneous emission. Anyway, nothing can be done, you have to live with this. And so these are some of the important issues which I have put in a chirp pulse amplification system. Okay. So in the bandwidth preservation and gain narrowing. So as you would have understood till now, I have emphasized so much on the bandwidth preservation. We don't want any clipping, we don't want any loss to the bandwidth. Okay. All those frequencies have been given a group velocity dispersion, the dispersion which is important for getting a long pulse, but we don't want to reduce the bandwidth. And gain narrowing. Gain narrowing, I think I'll just explain a little bit what I mean by gain narrowing. Gain narrowing is, suppose my gain medium has a gain of this kind. This is the frequency, and this side is of course the amplitude or intensity, you might call it. So different frequencies have different gain. So each of these lines correspond to different frequencies. So you can see the ones on the extreme corners of this curve, they don't have much gain. This frequency also does not have so much gain, while the one in the center has the maximum gain. So what will happen is, all those the center frequency, in case of ND glass it is 10.6 micrometer, in case of titanium sapphire it is 800 nanometer. So that is the central frequency. The central frequency will have the best gain, and it will keep growing, while this, so this is my pulse in time. This one picks up this frequency and it grows, while the ones at the side are not able to grow as much as this, but they will feed into this. Okay. So if I have this, my gain profile, because the central frequency has taken up all that I had described this whole thing before. In the gain, there is a hole here, because this pulse has taken out all the gain from that central frequency. This is frequency. And these have just added to this hole here. Okay. And they add and they fill up that hole, so that the pulse, when it comes back again, it is able to get gain from this central part. But what has happened is that these frequencies on the wings have stopped growing. Only the central frequency is growing. And so each time your gain has narrowed down. So instead of being a curve like this, it has become a narrower curve, because these outer wing frequencies have fed into the middle one, and that has stopped growing. So it is gain narrowing is one more problem. Gain narrowing means again a loss of bandwidth preservation. You are not preserving the bandwidth. But this is an inherent thing of not just regenerative, it is more highlighted in a regenerative amplifier, but it happens even in the linear amplifiers, like say here, amplifier 1, amplifier 2 here. So you have this oscillator pulse, you have a pulse selector, you have selected the pulse, then you go into a regenerative amplifier where you boost the energy to a large level, and then you go on adding some other amplifiers which are called linear amplifiers, because there may be just one pass or two pass at the most from each of these, and it extracts energy. But at each of these amplifiers, these issues crop up. And spontaneous amplified spontaneous emission I spoke of in the regenerative amplifier. It is mainly in the regenerative amplifier, not so much in these following amplifiers, okay, where you get that Q switched pulse at the bottom. That is the amplified spontaneous emission. Okay. And then you can have a stretcher compressor mismatch. Okay. So you have that. All these effects, the temporal pulse shape of the final compressed pulse and the obtainable intensity. So you have to kind of live with all these problems and see how you can balance it out.